Hi everybody, thank you for coming to watch this Canyon Academy Physics video. In this video we're going to be covering the Physics 112 concepts from week 11, which include thermal radiation, blackbody radiation, quantization of light, and the photoelectric effect. So the first thing that we're going to talk about is thermal radiation, and thermal radiation is necessary to understand in order to continue on with blackbody radiation. And so the most common example for thermal radiation is the sun. And the sun just emits electromagnetic waves, and the frequency and the wavelength of these waves is always dependent upon the temperature and the material in question. And so if you consider what occurs at absolute zero, which is just theoretical, we can't actually achieve absolute zero. But absolute zero is just 0 Kelvin. There's zero temperature, meaning there's no kinetic energy that's actually occurring. And so if there's no kinetic energy, then there are no interatomic collisions. And so whenever we have matter that with a temperature greater than absolute zero, then we're going to have kinetic energy, and thus we are going to have interatomic collisions. And so whenever we increase the amount of kinetic energy, so we're increasing temperature, we're going to be having a change in the number of interatomic collisions. And this change is going to result in the acceleration of the charge, in the acceleration of the particles in question. And so we know that from past weeks that whenever we have an accelerating charge, we're going to have the production of an electromagnetic wave. And so this is essentially how thermal radiation is conducted. We're having an accelerating charge due to the increasing number of interatomic collisions. And so basically how this relates to blackbody radiation is that blackbody radiation is just thermal radiation from a black body. And a black body can be considered as any physical body or object that absorbs all electromagnetic radiation. And so once it absorbs all that electromagnetic radiation, it's going to emit it according to Planck's law. And Planck's law, we're going to talk about a little later, just tells us that the emission of electromagnetic radiation is determined by the temperature. And so this is seen on a spectrum, which we're going to show on the graph in the next slide. But what I want you to consider here is the model for a black body. This is what's most commonly seen as just a black box with a hole. And so according to the definition for a black body, this box is going to absorb all electromagnetic light, electromagnetic radiation. And so that's seen from this arrow entering into the black body. And then so once the thermal equilibrium is achieved, once the thermal energy, there's a constant temperature, the amount of thermal energy reaches thermal equilibrium, then we're going to have the emission of thermal radiation from the box that's equal to the amount of radiation entering the box. But this thermal radiation leaving the box is blackbody radiation. And so like I said before, blackbody radiation exhibits a distribution in energy that's dependent upon the temperature. So the amount of energy coming in the form of thermal radiation or blackbody radiation is dependent upon the temperature. And that's what we're going to see in the next slide here. Is in the top left, we have the blackbody radiation distribution graph. So from this graph, we can see that as the electromagnetic radiation intensity or energy is increasing, there's also an increase in frequency. And so what I want you to think about now is, and I'm going to show later, and how this equation was derived, but if you think about the energy is equal to Planck's constant times frequency, E equals hf, we see that with an increase in frequency, we're getting an increase in electromagnetic radiation to a point. So what was observed experimentally is that intensity, with an increase in temperature, we're having an increase in intensity of light up to a certain point. And this peak in the spectrum occurs at the end of the visible spectrum and at the beginning of the ultraviolet spectrum. And so what we also see here is that after this peak, we have a sudden decrease. And nobody could really understand why there was a sudden decrease after a certain point in this, and at which occurred at the ultraviolet light. And so the classical physics understanding was that whenever we're increasing the frequency, we should have an increase in intensity. So they predicted that as the intensity is increased, the intensity will continually increase with this increasing frequency. But obviously we can see that experimentally this was not observed. And so I'm going to take you over to this diagram right here. And so we see that classical physics says that this light should continually increase, that the intensity of this light should continue to increase. But modern physics and empirical observation shows that eventually it was going to decrease. And the solution for this, the explanation came when Max Planck derived the quantization for energy. And so he showed us that energy is equal to Planck's constant times F, h times F. And so he found that energy has a discrete value rather than being in a continuous range. And so this disproved the classical theory, and the explanation for this is a little bit difficult to understand. But if we're going to consider this black body box once more. And so we know that black body box, any black body will absorb all electromagnetic radiation. So that's what this line is showing. It's absorbing the electromagnetic radiation. However, at a certain point, if there's not enough appreciable thermal energy being created inside this box, we cannot have the emission of a thermal radiation or black body radiation. So at a certain point, which is this frequency here that occurs at the ultraviolet radiation spectrum. So at this point, there is not enough energy inside this black body to emit the thermal radiation, and so that's why we're observing a decrease in the intensity of the light. And so also what can serve to disprove the classical theory is that when you consider the law of conservation of energy, we know that we can't just have an infinitely increasing amount of energy, that energy cannot be created. And so you might be wondering why this is important to understand the quantization of light, of energy. And it's important for understanding our next topic, which is the photoelectric effect. And this photoelectric effect is just basically the fact that an incident light ray on a metal surface can cause electrons to be released. However, there are certain conditions to this, but ultimately the photoelectric effect serves to provide evidence for the particle nature of light. And so we know that the energy of electromagnetic radiation is quantized, and a quantum of energy is equal to h times F. And however, in order for an electron to be released, the energy of the light ray must be greater than the energy needed to release it. And so this energy needed to release it is known as the work function. And we know that once we have a certain amount of energy, once we have a certain minimum frequency value achieved for the light, we know that we can overcome this work function and create kinetic energy. Not create kinetic energy, but result in kinetic energy movement for the electron. So after a certain amount of energy is achieved, then we can see that the excess energy will be given to the electron as it is ejected from the surface. And so this is maybe a little bit better explained in this resulting graph. So we can see that until we reach this threshold frequency, we will not have any kinetic energy, because if we consider, let me draw on this graph. If we consider a frequency at this value, let's say, we know that E is equal to HF. So at this frequency right here, we're not creating enough energy. And so the amount of energy that we have cannot overcome the work function. And so what we need is, we need to achieve a light with a certain frequency in order to obtain energy that can overcome this work function and thus eject the electron with a kinetic energy. And so that's what's seen here. So once we reach threshold frequency, we have the available energy to eject the electron, which produces movement. So in this video we covered the thermal radiation, black body radiation, the quantization of energy, and the photoelectric effect. So if you have any questions, feel free to leave them in the comments.